Hi everyone. I am back with another video on my NSEM paper, which is paper review of theory of computation. Let's start without wasting any time. Here is the first question. Question one. Give notation of representation of the following components of the formal languages. First, alphabet, which is denoted as sigma. String, which is denoted as W. Empty string, which is denoted as epsilon. Next, length of string, which is denoted as W in modulus, and prefix and suffix are denoted as prefix and suffix with in a close brackets of W, and then language is denoted as L, and the operators and on language are different operators which can be used, which are union, intersection, star, and plus. Let's move to the next question, which is define FA, which is finite automata, and acceptance of the string by FA. The, the FA is a mathematical model used to recognize pattern within the strings. It consists of a finite set of states, a finite alphabet of inputs, a string, a transition function that maps states and input symbols to other states, a start state, and a set of accepted states. Acceptance of string by FA or finite automata, which is a string is accepted by a finite automata if the machine starts from its initial state and transits through a sequence of states according to the input symbols of the strings and ends on the accepted state. So it is been accepted. Let's move on to the next question, next part of this question, which is part C. Give core difference between NFA and DFA, which is non-deterministic or finite automata, and deterministic finite automata. Here we are define difference is between four different top subjects, which are transition function, acceptance criteria, states, and memory. In transition function and in non-deterministic finite automata, we can see that uh, have multiple transaction for a state on a same input symbol or epsilon state transition. In deterministic finite automata has only one and unique transition from a state of each symbol. Acceptance criteria. NFA accepts a string if there exists at least one possible path from the initial to an accepting state. As of DFA, accept a string only if there exists a unique path from the initial. In consideration of states, NFA can have multiple positions next states for each state and input symbols combined. In DFA, has a unique state next state for each state and input symbol combined. In terms of memory, NFA has capability of guessing and the correct path should use of epsilon transition. In DFA, lack of memory, each transition is unique, determined by the current state. Let's jump to the next question, which is question number 1, and which is part has D. We have to state true or false. So first is if L is a language accepted by NFA M, then L is also accepted by DFA. Yes, it is true. Every language accepted by an NFA can also accepted by DFA, as DFA has a subset of NFA in terms of computational power. Question and second part, for every NFA there exists an equivalent DFA that simulates the behavior of NFA. It is also true for every NFA there exists an equivalent DFA that can simulate behavior. In third part, in NFA to DFA conversion for n state, NFA there exists at most two n state in DFA. This is false, as in the NFA to DFA transition or conversion for NFA for an NFA with an nth state, there can at most 2 to the power n states is in the result of DFA due to power set construction. Let's hop on to the next question. Is the question 2, part A, which states that what are the regular set slash or regular languages? What are the valid operations used in regular languages? Here we define the regular languages. Regular languages are classes of formal languages that can be described by regular functions or recognized by finite automata. They are simple type of formal languages and can be generated by a regular grammar. Here are some operations performed on regular languages, which is union, concatenation, keying star, and positive closure and optionals. There are other options rather than this which are also being used. Let's jump to the next part. Here's the part where we have to fill in the correct regular expression for every language. Here's the first. For the first languages, which is 0, 1 and 1, 1, here is the regular expression which is 0, 1 or 1, 1. For the second languages, we can state as 0 to the power star as in regular expression. For the language, you can read this as A or B or epsilon in the second, A, B, epsilon, so on. You can read it. For the fourth one, there's the 0, 0, the whole star here 0 and double 0 whole star. For even palindrome, it is not possible to create an regular expression. Let's jump to the another part. Here we have to explain Adian's theorem. Adian's theorem states that for any regular expression R and string S, the solution to the equation x is Rx plus S, where x is a string variable can be expressed uniquely in terms of R and S. Here is our examples. You can pause the video and read it thoroughly to be explained. Next part of the question is here is the third question. Define the grammar for the formal languages. Complete the following table. Here's the table, and we have to fill all the parts here, which is for type 0, type 1, type 2, and type 3. You can pause the video and also read the following table for a better understanding of the question. Let's put on. Let's go jump to the next question, which is question number 4. Define the context-free language CFL and complete the following table appropriate with the appropriate grammar. Here is the definition of CFL, which is a context-free language is a language generated by a context-free grammar, which is a grammar where each production rule consists of a single non-terminal symbols on the left-hand side, and a string of terminals and or non-terminals on the right-hand side. Here's the some languages and its grammar. For the first language, its grammar is S denotes 0 S1 or 0 1. For the second, the grammar denotes this as S, which denotes 0S0 or 1S1 or 0011. For the third one, S denotes as 0S0 or 1S1 or epsilon or star. For the last, it's denoted as 0S1S or 1S0S or 01 or 10. Let's jump to the next. Here's the next question, which has a part A, which states that take a suitable example to demonstrate the following. For the first, we have leftmost derivation. The leftmost derivation in the binary tree, we first consider the leftmost side of in the derivation to be written as first. Here's the example. You can see and pause the video and read it thoroughly. For rightmost derivation in the derivation tree, we first consider the right side of the tree to be denoted as first. You can pause the video and read its example too. Then last is ambiguous grammar. Here's the example of the ambiguous grammar. You can pause the video also here and go through the example. Let's jump to the next, which is part B with reference to Turing machine. Define the suitable of the following. First, NTM, which is non-deterministic Turing machine. A non-deterministic Turing machine is a hypothetical model of computation that extends the capabilities of a deterministic Turing machine by following multiple possible transition from a given state on a given symbol. For DTM, which is deterministic Turing machine, a deterministic Turing machine is also a theoretical model of computation where machines' behavior is completely determined by its current state and the input symbol being ready with only one possible transition for each combination of state and input symbol. For LBA, which stands here as linear bound automata, a linear bound automata is a restricted form of Turing machine where the tape is bounded by an input size and only allowed linearly when many cells beyond the input. Let's jump to the next, which is question number 6. You have to give two examples of each of the following, which is decision problem, decision problem. For example, one, the halting problem, and this here we can see a second example for the decision problem is traveling salesman problem. For optimizing problem, we have knapsack problem and minimum spanning tree problem. You can pause the video and read the description in the given example. Let's jump to the next, which is undecidability, which first example is post correspondence problem and the second is tilting problem. For the part D part, which is DP and NP, where the examples are primary testing and integration factorization. You can here once again you can pause the video and read the description of every example. For the next, we have NP and NPC, where the two examples are subset sum and traveling salesman problem once again here. For recursive language, here the first example is even language palindrome and the second one is string with an equal number of zeros and ones. Once again, you can pause the video and read the description here. On to the next, we have question number 7, where uh, we have to explain some following things, which are smoky hierarchy, PDA, 2PDA, and NPDA, and recursively enumerable language. A smoky hierarchy is a classification of formal grammar languages and corresponding automata based on their expression power. It proposed by Norman Smoky in 1950s, and the hierarchy consists of 4 levels. You can see here as type 0, unrestricted grammar, type 1, context-sensitive grammar, type 2, context-free grammar, and type 3, regular language. Moving on to the P part, which is PDA, 2PDA, and NPDA. PDA stands for push-down automata. A push-down automata is a finite automation augmented with a stack, which also allows it to recognize context-free languages. Two-way PDA, which is known as two-way PDA or two-way push-down automata, is a variant of PDA or push-down automata where the stack can access from both the ends, from front and the back. In non-deterministic push-down automata or NPDA, and the NPDA is also a type of push-down automata that can have multiple positions of transition for a given state. Let's jump to the part C part here, which is recursively enumerable language. Here, we know as the recursively enumerable sets are the languages that can be recognized by a Turing machine. A language L is recursively enumerable if there exists a Turing machine that halts and accepts every in string in L and either halts and rejects or loops and indefinitely on string not in L. Here is my whole uh, paper review for EndSem. Thank you.